Okay, so next we're going to look at something called colligative properties. So in general, what a colligative property is it's a property where the value depends only on the number of solute molecules that we have in our solution, not on their identity. So if I dissolve glucose in something, let's say some water, let's say I've got a solvent is my water, and I add some glucose. If I add the same number of molecules of sucrose to another solution of water, its colligative properties will be the same, even though that's going to involve different masses of those particles. And while you may not know specifically the chemical properties of glucose and sucrose, the fact that they are different sugars implies that they have at least some different properties. But I am not concerned about those properties for the purposes of determining the colligative properties of my solution. So the ones we're going to talk about, how it affects vapor pressure. And specifically, we're going to talk about something called Raoult's law. Pressure. What did I do wrong there? I added some extra letters. Pressure. There we go. That looks like a real word. Then we're going to talk about freezing point depression. We're going to talk about boiling point elevation. And then we're going to talk about osmotic pressure. So in this first video, we're going to stick to the vapor pressure, and then we'll cover the other three in our second video. So let's talk about vapor pressure and how it's impacted by molecules getting in the way. So remember earlier, we were talking about vapor pressure in a previous chapter, where the idea is, let's say we have some water, and let's say we put this in a closed container, some type of seal. And what would happen is once we reach dynamic equilibrium, the rate at which molecules were vaporizing would equal the same rate that they were condensing back down. So every time a molecule went up into the vapor phase, another molecule would recondense. We're still having change. Individual molecules are still moving between the liquid and gas phase and the gas and liquid phase, but the overall amounts of molecules in each phase is equal once we reach dynamic equilibrium. And the pressure of those solvent molecules in this case, so the pressure of the vapor, is what we're calling the vapor pressure. Now that's just, for example, the vapor pressure of water would be just the pressure of those water molecules existing above in the gas phase. That's not talking about the air that may have already been in the container. So the only way the pressure in there would be equal is if we had like a vacuum when it got started, and other than the liquid, and then the water was turning gaseous. It was the only thing in there. If we could somehow remove all the other air, it's the only way we would get it to be the exact same pressure. So otherwise, we also have air contributing. But the pressure of just the water molecules, that's the vapor pressure. Now, how does a solute affect this? Well, if we look at the surface, so let's imagine we've got our water surface, and in the pure case, everything's a solvent molecule. So we're going to use circles to represent those, so everything can escape. But if I have solutes, let's say those are squares, they're going to take up some space at the surface. Depending on the concentration, will determine how many. Now, these squares, we're going to assume with all our colligative properties, we're going to deal with things that are non-volatile. So we're not worried about, does the solute evaporate? We're dealing with a solute that is not going to vaporize in any meaningful concentration that we dissolved in our water. To have vaporization occur below our boiling point, what had to happen was our water solvent molecule had to get to the surface, and if it had enough energy, it would be able to escape because it could pull away from the intermolecular forces keeping it there. But our solute molecule, he's happy right there. They're not going to try to escape. That means there are now fewer molecules, fewer sites where our solvent can try to get out. That means there's going to be less vaporization occurring. Because since the solvent is going to get away a little bit slower, there's going to be less gas, there are going to be fewer of the molecules in the gas phase, which is going to lower the vapor pressure. That means anytime, and I don't get to say anytime very often or always, we usually say, well, almost, but not really, but here I get to say always. When we have a non-volatile solute that we dissolve into a solvent, it lowers the vapor pressure of our solution. Now, how much specifically has a relationship that we call Raoult's law? So the vapor pressure of our solution, assuming again that it's not a non-volatile solute, is equal to the mole fraction of the solvent times the vapor pressure of the original solvent in its pure form. So for example, if our mole fraction is 0.99, So 99 out of 100 molecules is a solvent molecule. That means that our vapor pressure for our solution is going to be 99% as large. So we're going to take the vapor pressure of the solvent, multiply by 0.99. That's our new vapor pressure for our solution. Now, what does that look like? How do we solve something with that? What does that tell us? Let's look at an example. We're going to calculate the vapor pressure at 25 degrees Celsius of a solution that contains 42.5 grams of glucose and 300 milliliters of water. The vapor pressure of pure water at 25 degrees Celsius is 23.8 torr. We're going to assume the density of the water here to be 1 gram per milliliter. So, I need to find my mole fraction. That means I need to know the moles of the solute and the moles of the solvent, since those are both relevant to this. So to get that, I'm going to start with, I lost my pen, there it is, my 42.5 grams of glucose. That's a really big 6. C6H12O6. And I put something somewhere. Where did you go? There's my calculator. I need that. Okay, so we've got this. And when I find the molar mass in my periodic table, I get this as a molar mass of 180.18 grams per 1 mole of glucose. So if I convert that, I'm going to get that this is 0.236 moles of our solute glucose. Now, I also need to know this for water. So we have 300 milliliters of water. So first I need to use my density. I know that every 1 milliliter is 1 gram. Now, if you're comfortable enough with it, I'm perfectly fine if you were to just write 300 grams when you're solving this problem. But I'm doing this way because a lot of problems won't have a density of 1. You might work with ethanol or something, which doesn't have that same density, so then you'll have to actually show the math of the conversion. You can't just go, oh, the gram and the milliliter are the same. So you'd have to do this conversion step first. Then I need to use the molar mass. For every 18.02 grams of water, I get 1 mole of water. When I do this calculation, I'm going to get that this is 16.65 moles of water. Well, to use Raoult's law, I need the mole fraction of the solvent, and that's the water, not the solute, which is the glucose, which is what a lot of people are used to doing from other problems. They're just so used to, I've got to test for the solute. Well, no, here we want to know about the solvent. So we've got 16.65 moles on top for the moles of just this solvent. Then on bottom, we need to add together the 0.236 plus the 16.65 moles. We have to add those together. Let's make that look like an actual 3. That doesn't look any better. I'm just going to write below it. There we go. And when we do that, we're going to find that we get a mole ratio of 0.986. Then to finish my problem, I want to know the pressure of the solution, and that's going to be equal to the mole fraction, that's 0.986, times its vapor pressure, its pure vapor pressure, of it's just water, which is 23.8 torr. Notice this problem doesn't give you a specific unit to work in. There's no reason you can't stay in torr. Now, if the answers were a multiple choice question, all the answers are in atmospheres, at the end you would have to convert to atmospheres by dividing by 760. But here, because all the units work out, mole fraction is a unitless quantity, or as long as we're using a pressure there, we can use it in any unit we wanted to, as long as we know how to get there. So I've got 0.986, and I'm multiplying it by 23.8 torr. And I'm going to get that my new pressure for the solution that we're talking about here is going to be 23.5 torr. Now, a good check is that your solution should always have a lower pressure than the pure solvent. It does here. It's 0.3 of a torr smaller. And it's not a whole lot smaller because there's only a little bit of glucose compared to the water, which for a lot of solutions will be true. Because for a lot of solutions, you have a little bit of solute and a lot of solvent. But not always true. You could have one where you've got more solute and it's more like 0.9 or 0.8 or even 0.5 or something, depending on the way you set up your solution. But it's okay to only have a tiny change happen. That's all right. So that's how we do that. And this is really the main application we use for Raoult's law of how do we figure out the vapor pressure of a solution when we've dissolved something in it so that it's not the same as its pure solvent form. After this, in our next video, we will start looking at the other colligative properties. I'm doing 3 together because really boiling point and freezing point depression function basically the same way. So I like splitting it up this way. So I will see you in our next video.